Alright, hello everyone. Let's see. I am Professor Caudill, and today, picking up where we left off, we're going to start section 4.4. We're kind of blowing through this chapter, not surprisingly. But yeah, I'm going at a good pace, I think. So, uniform circular motion. So, centripetal. Centripetal, is that when it goes to the center? Okay, so I've never heard this term, tangential acceleration. All right, so type of motion in which an object travels in a circle at constant speed. Okay, so here we go. In one dimension. In two dimensions, it can be accelerating even if it's constant. Velocity is changing, so I think this means speed. Delta V over this. Okay, so I'm not exactly getting what they're putting down, but I see they're making a triangle out of this, so it's V. So this is, you could say this is like your V naught. This is your V, the next velocity. It's changed a little bit. So they're finding the difference here. So when delta t is infinitesimally small, then you get a derivative. All right, so we can find the magnitude of the acceleration. So this is just V. This limit as delta approaches 0, that's just V. So it's V squared. I don't know, not sure where they pulled out VR from. Probably over here. Okay, I see. So delta V turns into VR. Delta V is delta R. So they're pulling this out. I'm guessing R is the radius. So direction of acceleration towards the center. So that's centripetal. Centrifugal is when it goes outside, when it goes away from the center. So centripetal goes towards the middle. Centripetal Centrum, center seeking. Okay, so what are our equations? Our equations are a b squared over r and well, ac. Yeah. So let's try this. A jet is flying. Okay, we have a jet. It's about to enter a circular path. So V naught is 134.1. Gravity is 9 point. So we're going to solve for VA, so it's going to be 9.8. It might be negative 9.8. We'll see. So anyway, it's going to be this equals R. So R is so you have to know, like, we're dividing meters per second by meters per second squared. So I'm not sure if there's a time unit. Okay, so they're just getting meters per second. And I can see they converted meters to kilometers. I'm not sure. Like, I feel like I've gone back and forth through this book using negative 9.8 and positive 9.8. So I'm still, like, kind of figuring out what's most intuitive for me and if it matches the book. All right, let's try another one. Flywheel has 20, so R is 20. What is the speed of a point on the edge? Okay, so if it's 900 squared over 20, so that's 20. V, and that should be absolute value. Okay, so 2 times 9 is 18. What times itself is 18,000. So 3,000 times 3,000 is 9,000. So guessing approximately 4,000 is the speed. Might be off by 1,000 meters per second, but same order of magnitude. All right, so here we have common centripetal forces. I think the satellite in geosynchronous orbit is particularly interesting. jet in a barrel roll. It's 2 to 3 G's. Roller coaster is 5 G's. It's cool to know. Electron orbiting a proton is extremely fast. All right, so we getting into more math. Don't be threatened. Usually it's simpler than you appears on the surface. So equations for uniform circular motion. 420. So looks like this is the speed or the magnitude of it. Okay. So the magnitude of this vector so this is WT. So what's interesting about this is it's changing over time. And I also wonder if this is in degrees. Okay, so angular frequency. Radians. So mega is in radians. All right, so they are saying velocity vector of this, what is it called, uniform motion, uniform circular motion. Okay, so uniform circular motion, you're saying that's dr is negative a omega so you might be like, man, these are too many variables. Don't be alarmed. This is just being very abstract. So I wonder why they didn't just give r the position vector first, but we can find r by taking the integral of negative a omega and so that's going to be negative a omega. Now it's going to be the integral of sine omega t. So I'm thinking it's going to be plus cosine omega I'm thinking the I stays the same, hoping so. And then A omega, so that would be negative minus A, because the integral, no, actually it would be positive. It would be plus A omega sine omega t j plus some constant. So that's R of t, if you were curious. So as you can see, A is the magnitude of RT. If you're looking at the picture, if you're asking how this translates, A is the magnitude of RT. And you can see this is just doing trig. So Ka is adjacent over hypotenuse. So that's going to be hypotenuse. Don't know the hypotenuse. I'm trying to think how they would solve this. You could definitely do tangent theta. I'm just kind of like playing around with the math right now. It's not, I'm kind of getting sidetracked by the book. Hope you don't mind. So tangent theta is opposite over hypotenuse. So yeah, I was gonna change theta to W. I was gonna change theta to omega t, so it'd be tangent of omega t. But I think we should get back on track. So as we see, all right, so how is omega getting squared here? For differentiating it with respect to t, okay, cosine AT. Maybe it gets pulled out of the cosine function. Okay, it looks like it does. So that's something I didn't know. I mean, obviously, it's going to be... Okay, I see. They're doing the chain rule. So I know the derivative of cosine is negative sine. It is if you don't know, It's cosine. It's okay. So it's sine, cosine, negative sine, negative cosine. Okay, so if you're doing, let's say, yeah, so if you're taking derivative of sine, then you get cosine. Derivative of cosine is sine. Similarly, if you're taking the integral of cosine, you get sine. Integral of sine, you get negative cosine. So obviously, cosine x is negative sine x. We have to take that times that, and you get yeah, chain rule. Okay, so it's like I didn't know it, but I had a suspicion. So that's why. So I wonder if this was right. So we would have to do integral. Let's say if we're doing the integral of omega t. Okay, so we'll have to do a substitution. U is omega t. So du equals omega dt. So it'd be du over omega equals dt. Okay, so it will be sine u du 1 over omega. Okay, so then that would be 1 over omega. So that would be negative cosine omega t over omega. Plus a constant. Okay, so we understand how they're getting these numbers. So that's good. I wish they would have given us the position function, but no problem. So omegas would cancel out, wouldn't they? So that would actually be it would actually be negative a plus a and so that makes sense. Plus and b plus a constant as well. We can see it's starting to match this gradient here. So yeah. All right, so we have a big example coming up. Let's see what we can do. So proton is 5 times 10 to the 6 meters per second. R of P kind of looks like a gamma symbol. 175 meters. We're gonna find R at t times 10⁻7 seconds. Okay, so we know, so this is A. So we know it's 5 times 10 to the 6 is v squared over, so 0.175 is approximately 1.75 times 10 to the -1. Okay, so we're taking this divided by okay, so that'll be about, oh, let's say 6 times 10 to the 7. So square root both sides. So 6, we're going to round this up to 10 to the 8. So it would be 10 to the 8 times 1/2 power. So it's going to be 10 to the 4th is your 10 to the 4 meters per second is your velocity. So let's see if that's anywhere close. So it looks like they're doing a different way. They're taking frequency. Okay, so I used A equals v squared over r. They are using t is 2 pi r over v. So it's, I think my issue, or one of my struggles, is I just kind of blindly pick a function and test it out. I don't know if it's if it's just because I don't know the subject extremely well, but I think people that are really good at physics, they probably can pick out the right function immediately. But so like they read this problem and they instantly recognize they need to use the period of revolutions. Okay, so if that was the case, it'd be 2 to the -7. So what is this? This is about 6. 6 times 2, 10, 12, 10. Okay. So they're getting this number. Okay, so first they find the angular frequency. Okay, so all of this we could just put into a calculator. Okay. So thinking I should just start doing the calculator. Okay, so what are we doing? We want to do this, and then we want to do omega. Okay. I see they rounded it. Looks like they turned T is 2. Okay. All right. So, and then we want to do one seven five. So R cosine omega T R sine omega TJ. Okay. So we want to introduce a new symbol, omega. Okay, so and T, big T. Okay, so we're going to do two equations, equation 8, equation 9. T is 2 times pi times R. Times pi times R divided by V. So I know I don't need parentheses here, but for my peace of mind, I do it anyways. So next equation is omega is 2 times pi over T. Okay. So what do we want to call this? Time to complete one revolution. Okay. We don't want that yet. I'm just wondering why they kind of introduced these in a weird order. Like they don't even mention this anywhere. Omega is 2 pi over T. 2 pi over T. Okay, it's here. Okay, so where is 2 pi R over V? 2 pi R over V. I don't think they say anywhere. No, they don't. That kind of makes me upset. They kind of just pull this equation out of nowhere. Um, okay, we can call this the period. Period in uniform circles. Period in uniform. Okay, F9 calculates the frequency. No, then this is the frequency. I hope I'm spelling circular right. Circular, okay. Equation 9, 8. Okay. Let's see if these even display right. Okay, it looks like they're getting displayed right. 2 pi r over v, 2 pi over t. Period for uniform angular frequency. Okay. All right, good, good. Now we can do the more tedious part. Okay, so F8. So F8 is GT. So we're going left to right, top to bottom. So it'll be RR and VV. Pretty easy, just three variables. So we're solving equation 8. So we're going to solve T for T, R for RR, and V for VV. Okay, good, good. Now we do F9. That is going to be omega, omega. It's kind of a funny phrase. And TT. Omega, omega, TT. Solving this. Omega for omega, omega. And T is this. All right, now we add our dictionary. 8 is F8. 9 is F9. Okay, last part. So we're gonna do 8. So T is a period of motion. T is the and then R is just a radius, right? I really hope this is radius and not like the position. I'm thinking it's the radius. Yeah, I think it's the radius. Enter the radius. Enter the velocity. B speed. We don't need this. Results pt rr ev. Okay. I think we can run it now. So we're using equation 8. So we're doing solving for t, 0.175. So okay, so t is the period, 175, 5 times 10 to the 6. We get a big number. We get 2.2 times 10 to the negative 7, which is what they get. Our calculator is working. Now we need to add the next part. Do I even need to do that? Do I even need? Maybe I can just plug it in. Okay, if t is that. Okay. Maybe I'm trying to do too much. You don't want to do too much. Okay, so let's copy this for 9. So now we're doing omega. So enter the frequency. What is it called? Is it called frequency? Okay, omega t. T. E. Okay. Okay, so we're gonna copy this number. That's our period of motion. Copying this. Okay. Invalid syntax. Oh, what do you mean invalid syntax selected? You mean invalid syntax? Why? I don't know why this is breaking. Am I reaching like a limit? How many E-lifts I can do? E-lift has own code block. Okay, I know that. I know that. Maybe it's not indented, right? What do you want to? You mean to print something? Might have fixed it by deleting a random space. Maybe. Nope. And my display broke. Sorry about that. Maybe that maybe that fixed it. I guess the E-list just kind of broke. Okay, I think the E-list just broke. Very weird. Okay, so nope, result is not defined. Yeah, you want this here, don't you? Okay. Okay, what broke now? Results not defined. Okay. Does function 8 work? Okay, function 8 works. It's like the elif is just breaking right now. Why is it breaking? Okay, oh, something, okay. I think it worked. I don't know how I fixed it. Okay, so 9. Okay, why, why is it doing that? 9. Result is not defined. Okay, 8. Okay, elif, please. Result should be in that. When do we print or sometimes they print the result? Okay, so maybe this should be outside that. Maybe that was breaking it. Okay. Period of motion. Oh, and we okay. I think we fixed it. Jeez. So that's like it's a key example where yeah, it's that's where debugging the message the computer gives you does not help at all. The issue was that result was was out of place. Like I'm gonna add 2 lines that should separate it. Okay, so we're gonna copy this number. Man, that was a struggle. 9 mega, enter the period. Okay, so we're getting 2.8 times 10, 3, 6, 7. 2.8 times 10 to the 7. Is that what they got? 2.8 times 10 to the 7. Okay. So our calculator works. Absolute headache. Um, Okay, I don't know if I can do any more coding today. Five 5.7, where are they getting the 5.7? Okay, they're taking this. Okay. So it's RT is R cosine omega T I. Two minutes left. Like, part of me wants to make a function like this. R so position is region is R times cosine omega times T plus R times sine omega times T So what would this be called? Oh, I want that to be a 9, right? Function 10. Okay, we're getting paused. Uh, Not quite. Do I need to add an R here? Don't want that. Okay, so we're just gonna do R. Maybe I can just maybe I can just put it in here. I don't even need this. Okay. Let's try that. Okay. I don't know what that just gave me. Um Gave me a perpendicular sign. Okay. Try again. Senpai, make a symbol with arrow on top. Okay, this shouldn't be that hard. Okay. All right. 3 minutes over time. Really want to finish this before we. Okay, hey, there we go. All right. So equation 10. So we're gonna do something like that. Function R will be RR, get omega, PT. Okay, so we're gonna solve equation 10. Function R is R is RR TT 10 F10 okay 10 so what is that into the angular frequency enter the position. Okay, so R. Okay, now we need R. Oh, I messed up. Enter the okay, so this should be function R. Okay, function R. R is input. Enter the radius. Okay, T, enter the, what is T? To the time, and we need omega. It's R, omega. Okay. Send it. Restart. Oh, I need to do this, don't I? R, omega, T. Okay. So let's choose equation 10. Function R. Okay, enter the radius. Radius is 0.175. Angular frequency. So omega is 2.8 times 10 to the 7. Time is 2.2 times 10 to the negative 7. 2.2 times 10 negative 7. Okay, so we're getting 1.015. 0.015. So we actually need to add the unit vectors here. By symbol for unit vector I and j. Just the symbol. Okay. Okay. So let's see if we can try this again. Oh man. What is that? Rij? Not what I want. Alright, so this might be an example of we're trying to do too much. Maybe you can just do should be right times j times j times I. Okay, so okay, so ignore how it's so the radius 0.175, frequency is that, time 2.2 is 10 to the negative 7. So you're getting 1.5. Okay, let's try that again. Radius is 0.175. Angular frequency 2.856. Time 2.2 times 10 to the negative 7. Okay, so here we go. This is the right answer. 1.5 I hat minus 0.09. Our numbers are a little high. But I think this will serve our purposes for the most part. So thanks for hanging out. I think we can make progress today. I would hope so. So next time we'll pick up. So we're able to calculate this. It's just getting there is a little tricky. All right, thanks for watching. I'll see you.